In this video, we're going to be talking about factoring difficult denominators for partial fractions problems. And in this particular problem, we've been asked to use partial fractions to evaluate the integral of 4x divided by quantity x cubed plus x squared plus x plus 1. And we have this third degree denominator. It's a third degree polynomial. We call it third degree because the largest exponent here is 3. So it's a third degree polynomial. So this polynomial is a little bit more difficult to factor than our typical second degree polynomial, which is what we normally deal with when we have a partial fractions problem. So what I wanted to do is take the opportunity to talk about how you factor the denominator when it's a little bit more complicated than just, a second degree polynomial function. So there's a couple of things that you can think about. The first thing you want to do if you have a denominator that's difficult to factor is look for what's called the greatest common factor. So we'll say option number 1 is the greatest common factor, which we'll call just GCF. So if we have a denominator, for example, like 3x to the 6th minus 9x squared plus 3x, what we're looking to do is factor out a common factor from each term in this polynomial. And we're looking for the greatest common factor, which means we're looking to factor out as much as we possibly can. So right off the bat, we can see that we can at least factor out a 3, right? Because we have 3, 9, and 3. So we're going to be able to take out a 3. We know that for sure. But we can also see that we're going to be able to take out an x because there's an x variable in each one of these terms. So we can go ahead and take out an x, and let's see where that gets us. When we factor out a 3x, this 3 is going to disappear, and x to the 6th will become x to the 5th because we took out one of the x's. So we're just left with x to the 5th. Then we're going to say minus 3 because we took out a factor of 3 from this 9 here. 9 divided by 3 leaves us with a 3. So we still have minus 3. And we removed one x, so instead of having x squared here, we'll just have x. And then from this 3x term, we took out the whole thing. We took out the whole 3x. That doesn't mean that it can just disappear. That means we have to include here a plus 1. And remember, if you're ever not sure about a factoring step, you can always multiply your factors back out to see if you get back to your previous step. So we need to make sure we include this plus 1 so that when we say 3x times 1, we get this 3x term back. And now we should be able to see that there's nothing left to factor out of this x to the 5th minus 3x plus 1 polynomial. So we've factored as much as we can. And that's what we're talking about when we say we can pull out the greatest common factor. Sometimes our denominator can be difficult to factor because the denominator will be either the sum or the difference of two perfect cubes. So what we can say, this second method, we'll call the sum or difference of cubes, of perfect cubes. So for example, what we mean by the sum of two perfect cubes is 8x cubed plus 1. In this case, both 8x cubed and 1 are two perfect cubes, right? We can simplify this and say that this is 2x raised to the third power, and this is 1 raised to the third power, because 2x raised to the third, 2 times 2 times 2 gives us 8, and x to the 3 gives us x cubed, so we would get back to 8x cubed. So this is the sum of two cubes. Now, just looking at this on its own, 8x cubed plus 1, it might be difficult for us to factor. In the case of perfect cubes like this, when we have the sum of perfect cubes, what we need to say is that this is going to be equal to a cubed plus b cubed, where we've identified a equal to 2x and b equal to 1. If we can identify those two things, then the way that we want to factor the sum of two cubes is with this formula here. We say that a cubed plus b cubed is going to be equal to a plus b, quantity a plus b, times a squared minus a times b plus b squared. And then we just plug in what we've identified as a and b. So in this case, we'd get 2x plus 1 times a squared. So 2x squared is going to be 4x squared minus a times b, 2x times 1 is 2x, and then plus b squared is 1, so we get plus 1. We can also use the special formula for the difference of two cubes. So we said this formula was for the sum of two cubes. If we want to say the difference of two cubes where we can identify a and b, then that's going to be equal to quantity a minus b times a squared plus ab plus b squared. and we can factor it that way. So we want to look at greatest common factor. We want to see if we have the sum or the difference of two cubes. We have another option here where we can maybe use substitution to simplify our polynomial. So for example, if we're given the polynomial x to the fourth plus x squared minus 20, and that's our denominator, and we need to factor it in order to do a partial fractions problem, we can't factor this as is, but one thing we can say is that we can set u equal to x squared, and we can do a little substitution here. So substituting this in, we can see that we'll get u squared plus u minus 20. And this is something we can factor. This is just u plus 5 times u minus 4. And then at that point, once we have it factored, we can go ahead and plug back in for u to get this in terms of x instead of u. So we know that u is equal to x squared, so we say x squared plus 5 times x squared minus 4. And once we've subbed back in, we can see that x squared minus 4 can be factored further. So this becomes x squared plus 5 times quantity x plus 2 times quantity x minus 2. One other option, and this is actually the option we're going to be using to solve this particular partial fractions problem, is to factor by grouping our terms together. So we call this grouping. So for example, if we have the denominator x to the fifth power minus 3x cubed minus 2x squared plus 6, and we need to factor this. One thing we can do is group our terms together, pull out greatest common factors from each of the terms, and then see if we can factor from there. So here's what we mean. We're going to say quantity x to the fifth minus 3x cubed. We're going to group those first two terms together. Then we're going to group the second two terms together. So we have this minus sign in front. So we're going to say minus quantity 2x squared, but then we're going to say minus 6 because we had a plus 6 here. So we need this minus negative 6 to become a positive 6 to get back to our original polynomial. So we distribute that negative sign. Now we're going to pull a greatest common factor out of each one of these binomial terms. So what's the greatest common factor of x to the fifth minus 3x cubed? Well, it's x cubed, so if we pull that out in front, then we're left with x squared minus 3. And then if we look at the greatest common factor in this binomial term, it's just 2. So we pull a 2 out in front and we get x squared minus 3. And now at this point, you can see we're left with x squared minus 3 and x squared minus 3. So if we treat each of these as a term like this, and we say, what's the greatest common factor in these two terms? Well, the greatest common factor is x squared minus 3, quantity x squared minus 3. So we're going to pull that out, quantity x squared minus 3, and what we're left with is just x cubed, so times quantity x cubed, and then this minus 2 right here, so x cubed minus 2. And since both of these factors are irreducible, we know that we factored as much as possible. So with these methods in mind, let's go ahead and take a look at our partial fractions problem. So looking at the denominator in our partial fractions problem, we can see that there's no greatest common factor because these first three terms, the greatest common factor would be x, but that factor isn't shared with this plus 1 term here, so we can't pull out any factor other than 1, and pulling out 1 doesn't help us, so there's no progress we can make there. We don't have just the sum or difference of two perfect cubes, so we can't do anything there. We might be able to try a substitution, but we could really only make a substitution u equals x, and in that case we'd just end up with the same thing, u cubed plus u squared plus u plus 1. So we're not really going to get anywhere with a substitution, and so we want to try grouping. So if we look at this denominator here, let's group it into the first two terms, x cubed plus x squared, and then add to that the second two terms grouped together, x plus 1. We can see immediately there's no greatest common factor in the second term, so we can't pull anything out of there. From the first term, though, the greatest common factor is x squared. So pulling that out, we get x squared times quantity, x plus 1, and then we have, of course, this here, x plus 1. Now we can see that we have this common factor of x plus 1 in both of our groups, so we're going to pull that out, and we're going to say quantity x plus 1, pulled out in front, means we're going to be left with x squared, which we pull from right here, and then plus 1, which is the coefficient, the hidden coefficient in front of this x plus 1 term here, so x squared plus 1. Now our factors are irreducible, so we know we've done everything we can to factor. We can go ahead and plug those back into our denominator and start our partial fractions decomposition. So what we're going to say is we're going to have this fraction 4x divided by quantity x plus 1 times quantity x squared plus 1, and we're going to set that equal to, notice that x plus 1 is a linear factor, right? We have a first degree x variable, x to the first power. So when we have a linear factor, we just put a single constant over it, so a over x plus 1. And then we're going to add to that, and here we notice that x squared plus 1 is a quadratic factor because it's a second degree polynomial. The degree on the x variable is 2. So when we have a quadratic factor, we have to add bx plus c. We start with b because a was taken. So we have bx plus c divided by x squared plus 1. Now we're going to multiply both sides of this equation, this entire equation, by the denominator from the left-hand side. So we're going to multiply by x plus 1 by x squared plus 1. So both sides get multiplied by the denominator from the left, and that's going to cancel completely the denominator on the left-hand side, and we're just going to be left with the numerator 4x. Then that's going to be equal to, here when we multiply this whole denominator by a over x plus 1, the x plus 1 terms will cancel, and we'll just be left with a times x squared plus 1. When we multiply this by our second fraction, bx plus c over x squared plus 1, the x squared plus 1 factors cancel, and we're just left with this x plus 1 here. So we get plus quantity bx plus c times x plus 1. So from here, we'll go ahead and multiply out the right-hand side, and we'll get ax squared plus a plus, multiplying these polynomials together, we get bx squared plus bx plus cx plus c. And now we want to collect like terms, so we'll end up with 4x is equal to, looking at the x squared terms, we're going to have ax squared plus bx squared, which is the same as a plus b, quantity a plus b, times x squared, and we've dealt with these two. Then we want to look at our terms involving x, which is bx and cx here. So that's the same as plus quantity b plus c times x, and we've dealt with these two. And then we have our two constants here, a and c, so we get plus a plus c. Now, equating coefficients on the right and left-hand sides, essentially, remember we have 4x over here. Basically what we have is we have, on the left-hand side, 0x squared plus 4x plus 0. And so when we equate coefficients, we're looking at the coefficients in front of each of these terms. So this is the coefficient on the x squared term, and we match it up with the coefficient on the x squared term. The coefficient on our x term, which we match up with the coefficient on our x term, and the constant, which we match up with the constant. So we're just matching the left and right hand sides. These are going to give us our system of linear equations. So we're going to take the coefficients, set them equal to each other. So we know that a plus b has to equal 0. So a plus b equals 0. We know b plus c has to equal 4. And we know a plus c has to equal 0. So we need to use these three equations to solve for our constants a, b, and c. Let's take this third equation and find a value for a in terms of c. So we'll subtract c from both sides, and we'll get a is equal to negative c. We'll go ahead and plug negative c into our first equation here. So we'll end up with negative c plus b equals 0. And then here we have b plus c equals 4. So flipping those around, we have c plus b equals 4. And now what we can do is add these two together like this, because we have a negative c and a positive c. So when we add these two together, we'll get 0. Positive b plus positive b is 2b, and 0 plus 4 is going to be equal to 4. So now we can see that we have b equals 2, and we've solved for our first constant. So knowing now that b is equal to 2, let's go ahead and solve for either a or c. If we plug our value for b back into this equation right here, we're going to get a plus b, or a plus 2, is equal to 0, which means that a is going to be equal to negative 2. So a equals negative 2. And we already know that a is equal to negative c. So multiplying a by negative 1, we find that c is equal to positive 2. So now we have all three of our constant values a, b, and c, and we can go ahead and plug them back in to our partial fractions decomposition, which is of course right here. So we're going to plug it in to that right hand side, and what we're going to get is the integral of a, which we know is -2 over x plus 1, plus bx plus c. So we know b is 2, so we have plus 2x plus c. C is 2, so we get plus 2, and we divide that by x squared plus 1 dx. Now that we have our new integral, we can go ahead and start simplifying. So the first thing we want to do is break the integral into two separate integrals. So we're going to get the integral of -2 over x plus 1 dx, and then add to that the integral of 2x plus 2 over x squared plus 1 dx. And we can start simplifying. So we'll factor out a -2. We'll get -2 times the integral of 1 over x plus 1 dx. And then here we'll factor out a 2 from the numerator. So plus 2 times the integral of x plus 1 over x squared plus 1 dx. This second integral we can go ahead and break apart again, so we're going to leave this integral as is. This second integral, though, is going to become plus 2 times the integral of, we're going to take just one term at a time from the numerator, which we can do. So we can say x over x squared plus 1 dx, taking just this term. And then add to that, we have to remember to distribute this 2, so we have plus 2 times the integral of the second part of our numerator, so 1 over x squared plus 1 dx. Now you can split things like this when you have multiple terms in the numerator. You can't split apart terms in the denominator, so we couldn't separate these x squared and 1 terms in the denominator. We can only split apart terms in the numerator, and we'll have here -2 integral of 1 over x plus 1 dx. Now our first and third integrals are easy to evaluate. Our second integral, though, we still need u substitution. We're going to go ahead and say u is equal to x squared plus 1. Taking the derivative of that, we get du is equal to 2x, and of course we attach dx to that. And then because we recognize that we have an x dx here inside of our integral, and those are both in the numerator, we can go ahead and solve this for x dx by dividing both sides by 2, and what we'll get is x dx is equal to du over 2. Now with this information, we can go ahead and evaluate each of these integrals. So the first one, when we have 1 over a linear term here, so we have a first degree polynomial, we have x to the first power. When this polynomial is linear, we can take natural log of the absolute value of the denominator. So the integral becomes -2 times natural log of the absolute value of x plus 1, and that's our first integral. The second integral, we have to say plus 2. And now here's where we make our substitution. So we know that x dx is going to become du over 2, so we're going to have the integral of du over 2. We also have, though, now 1 over x squared plus 1, and we said x squared plus 1 was u, so we have 1 over u times du over 2. Our third integral we're going to evaluate with a formula. Whenever we see 1 over x squared plus 1 inside our integral, the formula for that is always the inverse tangent function, or tangent to the -1 of x. And that's only when we have this exact format here, 1 over x squared plus 1. If this is different in any way, then the formula looks a little different. But in this case, we have the exact value that we need for this formula. So we're going to say 2 times the inverse tangent function, tangent to the -1 of x. And of course, we have to add c to account for the constant of integration. We want that at the end. All we have to do now is evaluate this middle integral and back substitute to get this in terms of x instead of in terms of u. So what we'll do is first notice that we have a 2 in the denominator here that we can cancel with the 2 in this numerator, and we're just left with 1 over u times du. And of course, because u is a linear factor, because u is a linear term, we can say the natural log of the absolute value of u. So we get -2 natural log of the absolute value of x plus 1 plus the natural log of the absolute value of u. Well, we said that u was equal to x squared plus 1, so we're going to get the natural log of the absolute value of x squared plus 1. However, remember that the absolute value of x squared plus 1 is always going to be positive, because no matter what value you plug in for x, whether it's positive or negative, once you square it, x squared will be a positive value. When you add 1 to that, you'll still have a positive value, so there's no way that x squared plus 1 will be negative, which means it's really redundant and unnecessary to write these absolute value brackets here. So we can just say natural log of the quantity x squared plus 1 and just drop the absolute value. And then we just add our last term to inverse tangent of x plus c, and that's it. That's how you use partial fractions to evaluate an integral when we have a denominator that's a little bit more complex.